So Elasticsearch is a great search engine, but Yelp was not happy with its performance and hence they built their own HTTP layer on top of Lucene. In this video, we take an in-depth look into the architecture, performance improvements and key design decisions that Yelp took while reconceptualizing their own search engine. But before we move forward, I'd like to talk to you about a course on system design that I've been running for over a year and a half now. The course is a cohort-based course, which means I won't be rambling a solution and it will not be a monologue at all. Instead, a small focused group of 50 to 60 engineers will be brainstorming the systems and designing it together. This way, we build a very solid system and learn from each other's experiences. The course is enrolled by 800 plus engineers spanning 12 cohorts and 12 countries. Engineers from companies like Google, Microsoft, GitHub, Slack, Facebook, Tesla, Yelp, Flipkart, Dream11 and many more have taken this course and have some wonderful things to say. The course is focused on building systems the way they are built in the real world. We will be focusing heavily on building the right intuition so that you are ready to build any and every system out there. We will be discussing the trade-offs of every single decision we make, just like how you do in your team. We cover topics ranging from real-time text communication for Slack to designing our own toy load balancer to ClickBuzz's live text commentary to doing impressions counting at scale. In all, we would be covering roughly 28 systems and the detailed curriculum split week by week can be found in the course page linked in the description down below. So, if you're looking to learn system design from the first principles, you will love this course. I have two offerings for you. The first one is the live cohort-based course and the second one is the recorded offering. The live cohort-based course happens once every 2 months and will go on for 8 weeks, while the recorded course contains the recordings from one of the past cohorts as is. If you are in a hurry and want to binge learn system design, I would recommend going you for the recorded one. Otherwise, the live cohort is where you can participate and discuss the systems and its design live with me and the entire cohort. The decision is totally up to you. The course details, prerequisites, testimonials can be found on the course page arpitbhayani.me/masterclass. I repeat, arpitbhayani.me/masterclass, and I would highly recommend you to check that out. I've also put the link of this course page in the description down below, and I'm looking forward to see you in my next cohort. Yelp is a website where businesses list themselves, people engage with them for their services, and post reviews about them. Now, to make discovery better, Yelp used to use Elasticsearch, but they soon built their own. Why? Why did it happen that Yelp had to replace Elasticsearch? Now, the first reason that they provided is that Elasticsearch does document-based replication. Now, what does this mean? This means that, let's say, you have your search service which is powered by Elasticsearch, and on Elasticsearch cluster you have 3 nodes, right? And in Elasticsearch, when you configure an index, you have to specify the number of replicas of it. So now what happens? Let's say you index a document. The write goes to the primary replica or the primary node, right? From there, the replication kicks off and that same operation is applied on the replica node. Right. So now let's say if you index a document in one, let's say this is the primary node. When you index a document there, now the same operation would be done on replica, which means that when you are writing something, when you are indexing a document, the write operation not only happens on the master, but also on the replica. Now this means that because the same index operation is going to happen there on the replica, which means that if I would want to scale up, I would also need to scale the CPU power of it, because obviously indexing a document requires you to process the text, split it, put it into inverted index and whatnot, right? There is a lot of work that needs to be done. So what does this mean? This means that when you are scaling out, it just does not mean that add more nodes with cheap CPU or with low ranked CPU. Here also, just because you want to support high write load, your replica also needs to have enough CPU capacity. Now this means that scaling out is not cheap. It comes with its own cost, right? That is reason number one. Reason number two is that there is an uneven load distribution. Now here we see there are multiple data nodes on which the data resides. So these are physical servers on which the data reside. But what could happen is, let's say, when you're creating an index in Elasticsearch, you specify the number of shards of that index. This is independent of the number of nodes that you have in the Elasticsearch cluster. So I may have an index having 5 shards, but split across only 3 nodes, which means that there is a chance of having uneven distribution. Let's say there is a logical shard in Elasticsearch, which is very heavily queried, which means, and let's say a couple of them, they all are put into this one Elasticsearch node that you have. So which means that there are chances of uneven load distribution, and some shard, some physical data node would become more hot. It would become hotter than others because of this uneven load distribution. So when such things happen, this is typically what which is typically what engineers do when there is an uneven distribution. They use the Elasticsearch head plugin, and then they do reallotment of shards across physical data nodes, and the data gets copied and the load gets distributed there, right? So this is typically manual rebalancing is required in that case. Third reason is auto-scaling is challenging. You would have heard that with Elasticsearch, most probably when people use Elasticsearch, they always provision for peak. I've been in situation multiple times. So we always over provision our Elasticsearch cluster, and we are always provisioned for the peak, even though in most cases we don't see that much of load, right? So that is where the problem is. Why? Because auto-scaling is not easy with Elasticsearch. That becomes a problem, because spinning up an Elasticsearch node where it gets data copied and whatnot, it takes a lot of time to do that. Plus rebalancing, remigration of data, a lot of things happen behind the scenes, which is why it makes auto-scaling really complicated when it comes to Elasticsearch. So these were the three critical reasons why Yelp thought of, hey, we can't use Elasticsearch, it's not performant, let's build our own search engine. So obviously what they did is they wrote their own layer instead of Elasticsearch. Now first we need to understand what Elasticsearch actually is. So Elasticsearch is actually a search engine built on top of Lucene. So Lucene is the one that powers the actual inverted index and ranking and whatnot. So Lucene is the actual search engine. Elasticsearch gave a very nice user-friendly HTTP JSON based endpoints on top of that. So that is what Elasticsearch is. So which means every node of your Elasticsearch cluster internally is actually running Lucene to do this. So Lucene is not a separate server, but it's a library that does this file management, inverted index management, ranking and whatnot. So which means that you can keep Lucene as is and rewrite the HTTP layer which Elasticsearch provides. So what Elasticsearch does is makes using Lucene simple by exposing HTTP endpoints and distributed, because cluster management on Lucene does not support that. Lucene is just single node search engine, right? Elasticsearch makes it distributed. Plus it had other features like replication, sharding, learning to rank, custom fields, analytics and whatnot, right? But most of these features Yelp did not really require. Obviously some of them yes, but not all of them. So what Yelp is doing is Yelp re-architected this part. They kept Lucene as is and they replaced Elasticsearch, like the HTTP layer that Elasticsearch provided. They used Lucene and they built their own HTTP layer on top of Lucene, which is what they are calling nrtSearch. So what they wanted to leverage? They wanted to leverage two key features of Lucene. First is the near real-time segment replication. So let's go deeper into Lucene and what it actually does. So Lucene has something called as segments. Each segment, now segment is where the actual data resides. So for example, if you have indexed 10 documents, the 10 documents are stored in a segment, right? And these segments are immutable, which means that once a segment is created, it is created. It would not alter, right? So that segment is immutable. So what happens is, let's say you have a Lucene node and you have a primary and a replica in Lucene if you'd want to do that. So because segments are immutable, whenever a write happens, whenever you update a segment, whenever you create a new segment, a replica node can literally just pull this segment out because it is immutable. Nothing would change there. It can literally just pull this segment out in one shot and, it would copy the segment from the primary node into the replica node. And then replica can start serving its request for that particular segment. So this makes scaling very fast and efficient. So which means that once the segment is created in the primary, the replica node can just make an API call or just access it, because it's a physical segment on the disk, and just copy it and basically copy it to its disk, making it much faster to do this. So there is no need of explicit reindexing of the data. Like in Elasticsearch, we had to reindex on every replica. Here there is no need of doing that. There is no need of reindexing because the data is already indexed and stored in segment in the form that is directly consumable. So that's with this, what implies that if I want my replica to start serving the request, it does not have to do reindexing of the document. Instead, it just have to copy the segment from its primary node into the replica node. Much efficient. This is feature that Lucene provides, but Elasticsearch is not using, right? So which is why Yelp thought, we need this feature, we'll write our own layer. Second reason is concurrent search. Obviously, Elasticsearch is also concurrent, but because the search happens on segment, because segment is the entity where your inverted index are stored in Lucene, if you have 3 segments, I can make 3 parallel queries on 3 individual segments and then get my queried answer, or rather get my search query's answer, right? But this is not possible with Elasticsearch, because in Elasticsearch you have a replica in which all the data is there, because it has abstracted those things out for simplicity. So here, in order to leverage multiple cores, you can actually fire parallel queries over segments in the same node, making it much more efficient. So these are the 2 features that Yelp wanted to leverage of Lucene, which Elasticsearch abstracted, right? Obviously, they did it for the betterment, for the ease of use, but Yelp wanted that near real-time performance out of it. So now let's see how Yelp implemented it. This is where, just like how Elasticsearch is an HTTP layer on top of Lucene, what they used is Yelp used a project by some guy named Mike. It's called Lucene Server Project. Now this Lucene Server Project, there is I'll link the blog in the description down below. You can check out this source code. It's not that difficult to understand. You can skim through it quickly. So Lucene Server Project is the HTTP layer on top of Lucene. Now this Lucene Server Project, just like how Elasticsearch provided HTTP layer on top of Lucene and named it Elasticsearch, so Lucene Server Project is the HTTP server running on top of Lucene. So you would have a Lucene index there and it just provides an HTTP interface, basically making it simpler for you to talk to it, right? So the key implementation details. First, using gRPC. So what Lucene server does not support gRPC. It's normal REST based thing. But what Yelp did is they thought, hey, we should not be using REST and JSON because it's not that efficient. So they rewrote their interface layer and they used gRPC and protobuf. gRPC protobuf makes it really simple, really fast, really efficient because it saves a lot of time to do serialization and deserialization of the data. So which is where what they did is they replaced the HTTP/JSON layer and they replaced it with gRPC, and so that when your primary and replica, they have to sync the segments, or they have to, replica has to pull the segment from the primary. This all communication happens over gRPC. Right? But still, obviously, there would be some cases within Yelp where they would have to support REST and JSON because all the clients cannot just change all of a sudden to gRPC. Right? So, which is where they use gRPC gateway, which is a very famous library to create REST endpoints, REST JSON based endpoints on top of gRPC. So, it creates that code that you can directly run as a server and it basically masks all the gRPC protobuf details out of it. Right? So, you can still have your backend running gRPC. But while if you'd want to consume over REST/JSON, you can do that with gRPC gateway. And this generates a code which runs a server. gRPC gateway is not an entity. It's a library that does that. And whoever can directly talk gRPC can directly talk to this Lucene server because they have the gRPC layer there. They can directly talk to it and get their basically queries answered. Right? So that is great. So this is what their key design decision was. Next is about failovers, because obviously anything that could go down would go down and you have to be prepared for that. So now one key challenge that comes with architecting or just playing with raw Lucene is time it takes. Whenever node fails, for you to spin up a new node, it takes a lot of time. And typically the time is taken because when you start a new node and you would want to set up the Lucene on that or download those segments and keep it handy, what you would typically need to do is, let's say whenever a write comes to primary, you write it to the disk. Once a segment is created, you periodically back it up to S3 or your blob storage. And then when a new node boots up, that would download it from the S3, right? And then once the download is complete, it would start serving the request. This is the simplest approach that people do, which is what actually takes a long time for you to do failovers, because when a new node is spin up, it has to do a lot of network IO to get those entire segments downloaded and then start serving. So there has to be a better way. Which is where what they did is something really simple that we all use day in and day out. So Yelp is built on top of AWS. So what they use is they use EBS volume. So if you have used AWS, in case you haven't just checked the documentation, it's a brilliant one on EBS. So EBS is Elastic Block Storage, which literally plugs into any EC2 instance that you want. So what they did, when a node is running, let's say I started my primary node. when I'm writing, I'm not writing to the local disk of that server. Instead, I'm writing to EBS volume. Now, EBS volume is detachable and attachable to any other EC2 instance if you would want to. So which means think of it like your hard disk. You just plug out your hard disk and put it into some other machine. It would just start working fine. So which is what they did. So their nrtSearch, so they named their search engine as nrtSearch, which is near real-time search. And while writing it there, they don't write to the local disk of that server. They write it to the EBS volume attached to it. So which means if my primary node goes down, they just spin up another EC2 machine, which takes like 10 seconds. And then they just attach the same EBS volume there. So everything would just run immediately, like 12-13 seconds, and your server is up and running to serve it. It would not require you minutes to download the file and serve those things. So this is a very interesting approach that we all use day in and day out, but they leverage it so beautifully to make their failovers very, 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 very quick, right? So this made their recovery faster. It basically made them their boot time, normal server boot time, really, really, really fast, so that they can really start serving requests as soon as almost the server starts. In just a couple of seconds, they are done with that, right? Okay. So now the next challenge that comes in is around primary replica sync. So now here what happens is when you are writing something to the primary, when the index is created, now this needs to be notified to replica so that it can pull the data, right? Similar to how it happens with Elasticsearch, there is a duplication of operation on primary and replica. With Lucene, that's their key feature, right? So when you do the write happens on and a new segment is created. Once the segment is created, segments are immutable. So replica can just copy the segment onto the server and start serving it, right? So here what happens is whenever the write happens, whenever a new segment is created on the primary, this new segment, the primary notifies all the replica about it. That, hey, I am the primary, this is the new segment that is created. Replica would know about it, and then replica can pull the data from the primary. That entire segment will be copied onto replica. This way, the replication becomes, or the lag becomes really very less. Once the segment is created, it's literally copied to replica, and replica can start serving the request instead of doing reindexing on two different machines. Right? So this is really brilliant of the strategy, where they're actually using the core feature of Lucene that they always wanted to use in order to reduce the overhead of CPU or reindexing multiple times the same document. Right? Apart from this, for their search, which is nrtSearch, they also implemented a bunch of features that Elasticsearch provides, so that because they use Elasticsearch, there might be teams that would be using core Elasticsearch features, which is where they added a bunch of features on top of their own, or in their own implementation, which is nrtSearch, so that they come very par to Elasticsearch, right? But they were not really very fancy, and they were more focused on search versus analytics. So because they were rewriting it, they could prioritize what to implement and what not to implement. Okay, what next? Performance improvement. So the first one is called as virtual sharding. So we know that in Lucene there are segments, and search happens over segments, right? So the data is stored in segments, the inverted index are part of segments, and search happens over segment. Now, the worst thing that you can do is allocate one search thread for one segment. If you do this, now let's say there are hundreds of segments, and to do concurrent search across all of them, if you allocate one search thread for each segment, that would have you incur or create a lot of threads. Now, obviously there has to be a cap to the number of threads that you do for concurrent searching, right? If you create a large number of threads, it would make your operating system run out of memory and your process crash. Right? Which is where what do is they introduced a concept called virtual sharding. Now what virtual sharding does? So instead of having one search thread for every segment, what they do is they club multiple of them and allocate them to one search thread. Now this way, and the way the allocation happens is a pure greedy approach, which means that they sort the number of segments by the number of document it contains and allocates them such that there is a consistent work across all the search threads. This way, it allows you to leverage the power, the computation power that you have, the memory that you have in the most efficient way. So this is the concept of virtual sharding, which means they are virtually sharding the segments into slices, and which is what they call the group of segment is basically slices, and search thread is allocated to a slice, right? This is a way to ensure consistent work across, right? Second optimization is basically parallel fetching of document fields. This is a classic one where you might have documents stored at one place. Now, when you would want to fetch the document with the actual detail of the document, you may do it in parallel, which is what the second optimization is all about. And the third one is about segment level search timeout to maintain consistent SLA. So now when you are searching within a segment, right? So when you're searching on a segment through which lies within a slice. Now slice is just a virtual concept, right? It's just a virtual chart. So when you're searching on a segment, there has to be an SLA that you maintain. Let's say if it is taking you 5 seconds, 10 seconds, worst case, to search within it, you can't just let your client wait for a very long time. Which is where what you do over here is you have timeouts that you have applied on segment level searches. This way, you say that, hey, if you don't return, or like if this thread does not respond in this n milliseconds, you would just go with an empty response from that segment. Obviously, you are gathering data from multiple segments, but from that one segment, if it is not meeting an SLA, you would be going past it. Right? This is typically done to ensure that you have consistent SLA on the client side by compromising on the correctness of your information. Like you may not be searching across all the document because one of the segment took time. You are not just letting your client wait for a long duration. You are introducing timeout over there, right? Now let's talk about migration. So obviously building is fine, but now they had to do seamless switch from their existing Elasticsearch load to this nrtSearch that they built. So now what they did is they used to have, or they built their own proxy layer called Apollo proxy. This is the Elasticsearch proxy that they built and they used. So by default, all the requests came to Apollo, which is their Elasticsearch proxy, and it went to Elasticsearch cluster that they had. But now what they were doing is they built nrtSearch, right? This nrtSearch is Elasticsearch like thing. So what they would want to do is they configured this proxy such that they would migrate or they would move some traffic to nrtSearch while most of the traffic to Elasticsearch to just test the correctness of the system. So what they first did something called as a dark launch. Now what is dark launch? This is an important concept that you should know as engineers. So dark launch is something where let's say you have built a system which is equivalent of some system. So now what you would want to do is you'd want to see if your system is giving out the same result as the old system. So you just don't launch it and make it available to the public because they might see wrong results. You are not sure that it is the exact same result that user would see no difference between them. So in that case, what people do is they send requests to both Elasticsearch as well and nrtSearch as well. But 5% request goes to new. So 95% request, so all request, 95% of request goes, 100% of request goes to Elasticsearch, but 5% of them goes to nrtSearch, and they compare the output of both of them. So if they are same, which means that so that they can test the correctness of the result on the production environment, right? So they compare the result for correctness. If they are good, then they increase the proportion. Then they increase from 5% to 10%, 10% to 15%, 20%, and so on and so forth, right? This is how they test the correctness of the system. So it does not mean user is seeing responses from nrtSearch. User is seeing responses from Elasticsearch only. Once they were sure about the correctness, they started to do this bifurcation, and now they started to move 5% traffic to nrtSearch and 95% traffic to Elasticsearch. And now the traffic that was moved to nrtSearch, users are shown response from nrtSearch. And then slowly they increase the percentage of nrtSearch and reduce the percentage of Elasticsearch. And slowly they migrated 100% to nrtSearch. So it's like a feature knob that they turned. So first they did a dark launch to test the correctness. Once they were sure, then they did a rollout, a phased rollout, 5%, 10%, 15%, and then slowly to 100%. Right? And this is how they beautifully architected and reconceptualized search on top of Lucene. Right? Just like what Elasticsearch does, they built kind of their own Elasticsearch, but specific for their needs. And this is what is brilliant about their design. Right? All of this thing that I explained is taken from their engineering blog, which I have linked in the description down below. Highly recommend you to check that out and go through the details of it. It's fascinating on what they did, how they did. Brilliant. Right? Again, highly must read for all of you. Great. So yeah, that is it for this one. I hope you found it interesting. I hope you found it amazing. I'll see you in the next one. Thanks a ton.